Hello again. I see now my sound's working, so that's good. It wasn't working a second ago. I'm going to run through this free response, number 163. This is a no calculator problem. Just based on what I read here, I'm pretty sure this is going to have something to do with accumulation, so that's good since that's what we've been studying. But this problem actually has a lot of good stuff in it. So on this slide, I'm going to read through the parts, and then one by one, we'll work through each piece as we go. So the figure above shows the graph of the piecewise linear, these are all linear segments, piecewise linear function f. For the interval -4 is less than or equal to x is less than or equal to 12, that's a closed interval. The function g is defined as g of x equals the definite integral from 2 to x of f of t dt. Okay, so that's g. Now listen, this picture is not g, this picture is f, but this picture is related to g. G is actually the area between the curve and the x-axis of this graph. All right, that's what they're telling us. Okay, so the question, so actually let me do something first here. So let me just do an example. If I wanted to do g of 6, g of 6 would be the definite integral from 2 to 6, right? Whatever I put in here goes up there, of f of t dt. So that means the area under the curve from 2 to 6. So that would be this area here. Now that's a triangle, 1/2 base times height. The base is 4, the height is 4, and so g of 6 would be 1/2 times 4 times 4. So that is 8 units, okay, 8 square units. I'm just giving you an example of what g is. G is an accumulation function that starts at 2 and goes this way for the values. If you go backwards, if you go on this direction, those are going to be negative. You have to treat those areas as negative. Okay. All right, now let's read through these 4 things and we'll do them one at a time. So letter A says, does G have a relative minimum, a relative maximum, or neither at x equals 10? And we're going to justify our answers. So remember, when we look at minimums and maximums, we're worried about the first derivative. And I'll show you how we'll handle that. Letter B says, does G have a point of inflection at x equals 4? Points of inflection occur where the second derivative changes sign. So we'll have to figure out what the second derivative of g is. Letter C says, find the absolute minimum value and the absolute maximum value of g on the interval, and notice this is a closed interval, -4 to 12. So we're going to use the extreme value theorem there. As soon as I know I'm looking for absolute extremes on a closed interval, I know that's the extreme value theorem. And then finally, we're going to find all intervals of g where g is less than or equal to 0. Find all intervals where g is less than or equal to 0. Okay, so let's go ahead and break these down one at a time. I'll do A on the next slide. So here we are. I just shrunk the picture down a little bit, but I'm going to answer the question, does g have a relative minimum, a relative maximum, or neither at x equals 10? All right, so we are going to focus on this point right here, x equals 10. Okay? And we need to find out what's happening with g. So remember, when we look for relative extremes, we typically make a sign diagram. And since we're interested in the point 10, I'm just going to make a sign diagram based on point 10 there. Now, the sign diagram should be on g prime. Okay? Let's figure out what g prime is. So let's go ahead and do the derivative here of g. The derivative of g is going to be g prime of x, and that's going to be the derivative of this definite integral. And thank goodness we have the fundamental theorem of calculus, and we call this part 1, which tells us, hey, if we're going to do this derivative, we just got to take this thing and stick it in where t is. And so that tells us that g prime of x is really just f of x. That is great news. that means our sign diagram is going to be on f. All we're doing is looking at the signs of the function on either side of 10. So take a look at this. What is the sign of function f on this side of 10, on this left side? That's not a very good circle there. So let's highlight this thing. Over on this side, on the left side here, what's the sign of function f? Meaning, is the y value above or below the x-axis? Well, the y value is below the x-axis. Oops. So that is negative. So this side, I'm making a mess of this thing, sorry. This side here, these are all negative values. So that means the slope of g is negative here. So g is going like this. Now, here's the deal. On the other side, we're still negative. The derivative does not change sign, which means we have neither a max or a minimum. G of x has neither a max or a min at 10. Okay? We're saying neither because the derivative of g, which is f, does not change signs. The derivative would have to change signs in order for us to have a max or a min. So the answer for letter A here is neither, and we've given support as to why that is true. Because the derivative of g is really f, and f stays below the x-axis on either side of 10. Okay, we checked letter A off the list. Let's actually ceremoniously do that. And now let's move on and we'll take a look at letter B on the next slide. So I've got a clean slate again. I'm going to highlight letter B here. Does the graph of g have an inflection point at x equals 4? In order for an inflection point to occur, the second derivative of g, the second derivative needs to change signs at 4. So I'm going to do a sign diagram on the second derivative of g. Well, let's think back to this. See, the first derivative of g, so g prime of x, equals f of x. That implies that the second derivative of g is actually the derivative of f. And since we have the graph of f up here, all we need to do is figure out how to find the derivative of f from this graph. Well, we learned that the derivative is just the slope of f. So what we're going to do is we're going to look at the slope of f on the left side of 4 and on the right side of 4 and make our sign diagram that way, right? Because we're doing the slopes of f, which is really the concavity of g prime. Okay, so do you agree that the slope over here, the slope over here is positive? That means that g is concave up, right? F is increasing, that means g is concave up. And over here, the slope of f is negative. That means the second derivative is negative, and that means we're concave down. That tells me that, yes, I do have an inflection point. G of x has an inflection point. At x equals 4. Yay! Okay. We figured out how to make the sign diagram of the second derivative, and then we discovered that, yes, we do have an inflection point. And we've justified our answer here, both with our calculations and with this awesome sign diagram. All right, I think that's good for B. Let's take a look at C on the next slide. Okay, so letter C is asking us to find the absolute min and absolute maximum values of g on the closed interval -4 to 2, and of course we have to justify our answers. All right, now what we are really going to do here is invoke the extreme value theorem, which tells us that we're guaranteed to have absolute mins and maxes on this interval. The extreme value theorem, which we usually call EVT in class because we're lazy. And, you know, in education, everything's an acronym. All right, so we're going to work with the EVT. The EVT says that we need to test endpoints and critical points. Okay, endpoints and critical points. So we already know our endpoints. I should say and critical points here. Sorry. I say stuff and I don't write it. So test endpoints and critical points. Okay, so I need to do G of -4 and G of 12. Those are my endpoints. I got to figure out what those values are. And then we have to figure out if we have any critical points. Well, remember, critical points are places where the derivative changes sign, right? The derivative changes, or derivative equals 0, actually. So we have 3 places where our derivative equals 0. Actually, we have 4 places. But 2 of those, the derivative doesn't change sign. So I am not going to worry about 2 or 10. All right? I'm only going to worry about -2 and 6 because those are candidates for extreme values. They are places where the derivative changes sign. So I'm going to have to figure out what G of -2 equals and what G of 6 equals. Okay, so how in the world do I find these function values? Well, don't forget, they told us what G is. G is this definite integral here. So for G of -4, I guess I should have wrote that over here. G of -4 is going to be the definite integral from 2 to -4, which is a weird direction, of f of t dt. Now, we don't typically like our limits of integration to be written that way, so let's just switch those around with a negative sign right here. That's our property that we have, and we're going to flip these around. And all this means is if I find the area from -4 to 2 and then make it negative, I've got the right value. So we need areas. I'm going to go up to the picture and I'm going to jot some areas in here. Let me erase these points now that we know we're testing those. Why isn't this working? Crap. There we go. Okay. Oops, I said crap right on the video. Sorry about that. All right, so let's do some areas. So we've got a triangle here. We've got a triangle here. There's 2 triangles. Actually, I don't need to make that 2 triangles. I can do that all in one spot here because we're starting at 2. So if I'm going from -4 to 2, this piece here is 1/2 base times height. So that is -2 times 4 is -8. That's -4, right? This is a -4. That means these are both 4, so this whole thing is 8. Okay, so the area of this definite integral right here is +4, but this little negative sign here means to make it negative. So G of -4 is -4, okay? Because I got to make this negative. Let me just erase that so that you don't think I'm crazy. All right. So we did that one. Let's do G of, what am I doing, 12? I got to do the area all the way out to 12. So that's starting at 2 all the way to 12, right? 2 to 12, f of t dt. Okay, so that one we can just start doing areas. So let me keep adding these on. So from 2 to 6, that's also an 8. This is a -8, so that's 0. And then this, again, is a -4 because it's just like that other one. So essentially, this guy is just -4 also, right? Because I've got starting at 2, right? We always start at 2. 8 minus 8 is 0, and then I got the -4 there. So this guy's also -4. All right, let's do 2 to -2. We've already got that answer on here, right? That we're going backwards, so this is going to be -8. And then 2 to 6, we've already got that answer on there. That's +8. Okay, so we're ready to make our answer. The lowest value right here, this is our absolute min at -8, and this is our absolute max at 8. So I would write something like let's just say G of 6 equals 8 is an absolute min, absolute max. and g of negative 2 equals negative 8 is the absolute min. And that's because of this extreme value theorem, right? The extreme value theorem says you test your endpoints and your critical points. I mean, the practice of using the extreme value theorem tells us we're going to check these places and pick the highest and the lowest. So negative 4 just isn't low enough because negative 8 is lowest, and negative 4 isn't high enough because 8's the highest. All right, so that's kind of what we do on that. And the key here is using our expression for g of x to find those y values of g, even though we don't have a picture of g. All right, so I love that question. It's got all kinds of awesome stuff from both semesters of class. We have one more question to answer, and then we'll be done with this video. Let's go to the next slide for letter D. Okay, thanks for your patience. We're going to knock out letter D here. Letter D says find all the intervals where g is less than or equal to 0. Okay, so for this one, remember we do have this formula that helps us find the values of g. And we just have to find all the places where we are less than 0. So I'm going to start by noting that g of 2 is the definite integral from 2 to 2 of f of t dt. That's 0. All right. Okay, so I already have a point where I am equal to 0. So 2 is going to be in part of my answer here. So this is what I like to do here. I like to think about this. So if I'm at 2 and I'm moving in this direction, I'm adding positive area. So we already wrote these numbers in. This is 8 here. I go from 0 to 8. I'm at 8 at 6 because we found out that was the maximum. And then we said this was negative 8. So that takes me back to 0 right here at 10. So I've essentially gone up 8 and down 8, but I've stayed above the x-axis for g the entire time. So this interval right here from 2 to 10, that is not part of our answer. However, back at 10 we're at 0, and then if we keep going this way, we're now more negative because this was negative 4. So part of my answer is the interval from 10 to 12. Because I start at 0 at 10 and then I have negative all the way to 12. So I know for sure I am less than 0 there. G of x is less than or equal to 0 because it's equal to 0 at 10. Less than or equal to 0 on 10, 12 for sure. Okay, now let's think backwards here. If I'm at 0 and I start going this way, we already said this was 8, but I'm going from right to left, so that's negative. So I'm negative 8 when I get to there. So I'm definitely negative on 2, and so that part there, that's 2 this way. And let's see how far I can go before I get positive again. I'm at negative 8, and then I start adding on negative area here, but I never make it back to 0. 8 and negative 4 is 4. And remember, it's negative 4 because we're going in the other direction. So all the way to x equals negative 4 in this whole region here, in this whole interval here, I'm negative. And then remember, I'm also negative here. All right, so this is all the way to negative 4. So on both of these intervals, on negative 4 to 2 and 10 to 12, g is less than or equal to 0. And we just, again, use those accumulation values that we wrote into the picture, the area values, to help us decide what's happening with g. And I like to start, right at my 0 point here and then move left and right to help me figure out whether I'm positive or negative. Okay, hopefully this gave you some insight into this problem. Obviously, I want you to try and get through as much as you can without me, but I know it helps to have a discussion about it. It's hard to sit around and be frustrated and stuck. We do want you to try to become more independent, to use your resources, to look stuff up, to make it happen, but I also like to help you out here because, I like talking about math. So anyway, have a great weekend. or if you're watching this during the week, have a great day, and we'll see you soon. Take care.